Welcome back. Last time we talked about the dynamics of carrier proteins, looking at the GLUT1 transporter, the glucose transport protein in red blood cells. So let's take a look at the mechanism of that and see how that protein works. So the glucose transporter is a uniporter specific for primarily glucose. It will move other sugars, but it's going to bind glucose much more efficiently than any other sugar molecule. So the red blood cells take up glucose by facilitated diffusion because and that works because the concentration of glucose in blood is much higher than the concentration of glucose inside the red blood cells in the blood. And so the GLUT transporter is an integral membrane protein. It has 12 transmembrane segments. So on a hydropathy plot that we talked about before, you'd see 12 peaks corresponding to 12 hydrophobic alpha helices that span the membrane. And the structure of those helices that span the membrane produce this hydrophilic cavity. So the R groups of these amino acids that line the cavity here, they're going to be able to bind to glucose. Now remember, glucose is polar and it's too large to diffuse freely, but it can bind in this hydrophilic pocket that's formed, or cavity that's formed in the middle of the GLUT1 transporter. So that's said to be the T1 conformation. And when glucose binds into that site, that cavity, a conformational change is induced, and we have the T2 conformation, which is when the cavity now faces, the structural change causes a cavity to face the inside of the cell, and that conformational change also causes a release of glucose. This is completely analogous to substrate binding and product release by an enzyme in terms of the kinetics, but obviously the glucose isn't modified in any way when it's transported. So this kind of raises an interesting question. Now, this will work in both directions, so it can move glucose out or glucose in. It doesn't discriminate between going out or coming in. All it cares about is the concentration gradient. So the question kind of that gets begged here is, what happens when equilibrium gets reached? Because if you've got more sugar in the blood compared to the inside of the cell, we're just going to reach equilibrium at some point, and that's no good. That doesn't help at all. If we need to keep moving glucose in, then we'd be looking at a mechanism of active transport to pump the glucose in. So how do we maintain this situation where we have low glucose concentrations inside the cell, but they're relatively high outside? Well, that's thanks to glycolysis. So what's going to happen is the glucose that gets imported from the blood into the red blood cell gets converted to glucose 6-phosphate, which is the first molecule that's going to go into the process of glycolysis, and so that requires ATP. We convert ATP to ADP, transfer the phosphate of the glucose onto the 6-carbon of glucose to produce glucose 6-phosphate, which is then pushed into glycolysis, and this is under the control of the hexokinase enzyme. So as long as you're converting glucose to glucose 6-phosphate, so what you're doing is keeping a low concentration of glucose in the cell, because the glucose is then converted to other intermediates in glycolysis, and so the concentration of glucose is kept low because we're feeding it into glycolysis. So it's much like bringing coal into the engine carriage of a train and then putting it into the furnace. You can keep bringing coal into the engine as long as you're putting the coal into the furnace, so there's space effectively for the coal. Here the space is the lower concentration of glucose due to its conversion to glucose 6-phosphate by hexokinase. So there's a little bit about the mechanism of the GLUT1 protein working in red blood cells. I'll be back soon.